Hello. Thank you. I already won. I work for notonthehighstreet.com in London. We'll talk about that later. You can find the slides online, unless, in case you don't see them, but they seem to be pretty visible. So this is a talk about how to make your Python code run faster. Why do we care about speed? Because we live in the age of low attention span. I have a low attention span of maybe 20 seconds early in the morning, then it just goes down a bit. And since we want results fast, I'm going to tell you that we are going to build up to this table, the magic table of not so slow anymore. It is not the whole truth, but it's an helpful heuristic. Why does our program run slow? Why slow? Because these machines have limited resources. They have some CPU, some memory, some RAM, disk. They are not infinite. So our programs, when we use all of one resource, we go slow. For example, when we use all of our CPU, the instructions just queue up, and you go slow. If you use all of your memory, as this helpful example shows, you get an out-of-memory error, and the operating system kills your process. That also happens a bit if you use up all of your disk. So you can run out of disk, and you get like disk full error. A much more frequent problem is using up all of your bandwidth. So basically, you're writing as fast as you can, or you're reading as fast as you can. Do you really need to wait for reading and writing something? Do you really need to say, OK, I write that file in full? Because when you're waiting, you're blocking, and the flow of the program doesn't go through. Network is even slower, especially if you use all of your bandwidth. And again, do you need to wait for the response? I know you probably don't even know what the API on the other end is doing. So how to tell why you're going slow? Well, you could log. I mean, that's helpful. Sometimes it's also helpful to know what your program is doing. And if you really, really need to know what your program is doing, the best thing is to profile it, as you all know. There's also a cheating, easy way. Just use a system monitor. My favorite is htop. And it's not going to always work, but you can see how much CPU is using, how much memory, and how much disk. And once you know why your program is slow, well, what you can do, there are a few canned solutions. You can parallelize it, so you can use thread processes. You can use async to have concurrency. You can use an alternative interpreter like Pypy, or you can push to C, and we'll see Cython in there. So once again, the magic table of not so slow anymore. And you see there's like different colors. Some are bigger wins, some are decent wins, and some are not wins at all. Waiting. Well, if you can run multiple operations at the same time, it means you don't need to wait. Well, the program will go on and do something, and then one piece of the program is waiting. The idea of concurrency is basically you can run multiple operations at the same time. The idea of parallelism, at least for the duration of this talk, is you can run as many of the same operation as you want at the same time. And if you can run more than one thing at the same time, well, you don't have to wait. An example of a parallel task. I'll ask Python where to find some things I care about. And Python asks the Google Maps API. And for this thing, I don't need to wait because I don't need to know where Berlin is to know where London is. I might have more problems with other things on that list. Classical sequential task, I need to know previous outputs to get the subsequent outputs, Fibonacci numbers. The first way to avoid waiting is to use threads. Ideally, if you can parallelize, you just import a thread pool, map your inputs through your operations, and you get outputs. In reality, sometimes you just need to create each thread manually, override the run command, and then start them. I like the fact that I didn't see, everyone is seeing my notes. Classy. How the thread works. They are an independent part of the program. The thread just goes on. The implementation sometimes depends on the operating system. Each part of the program shares memory with the caller, with the main thread. And they also share an interpreter, the Python interpreter. So you have limitations. Memory shared. If I want to write in the same memory location, I need to manually synchronize. And if you have ever used locks, well, you know they are messy. Also, the share interpreter has a performance overhead. So you encounter something called the global interpreter lock. And basically, you have only one interpreter that you can use. So threads are very useful. Well, threads are kind of useful for network and disk because you don't have to wait on I/O. They're not really helpful if you are running out of CPU or you're running out of memory. Processes are sort of the bigger cousins of threads. So you can use them to avoid waiting on disk and network, and also you can use them to use all the CPUs on your machine rather than just one. How do they work? Well, they spawn a new Python interpreter, which is a new operating system process. How do they spawn it? Again, the implementation depends. Sometimes it's fork. Sometimes it will serialize the input with pickle. Limitations, well, you're spawning a new process in the operating system, you're spawning a new interpreter, you have a startup time, you have the memory footprint of the interpreter, and you cannot share memory. Well, actually, you can safely share memory if you use these libraries. Things to watch out for while using processes: make your code importable. Otherwise, you're going to execute it every time. And avoid shared stateful objects like DB connections. Big wins, you can use all of the CPUs because the operating system will allocate one CPU to each new process and then shuffle them around like they were different programs on your computer. All of these concurrent operations in time, well, they are really good place to create a framework. So someone created a framework called Celery. Concept of celery is you have many workers, you can manage them, you have a shared task queue. A framework is more power, a simpler life, except at the beginning when you need to learn how to use the framework. The big takeout of celery is you can use multiple machines, because SQS or Redis, they will communicate between machines, so they're based on the network, so you can spawn your task to several different machines. Async, the not so new anymore hot new thing. There used to be asynchronous processing in older libraries like Tornado and Twisted. Now it's part of Python 3. How does async work? If you ever programmed a video game, maybe just something simple with Pygame, you know there is an event loop. And you wait for the user to give you some commands, and then you update the state of the game whenever the user does something. Async works in a very similar way. You have an event loop, and you attach some tasks to it. These tasks are called coroutines. The loop checks each coroutine for new event. If there is something, oh, there is a new event, so I'll react to that event. I'll execute some code, maybe I'll return the value, or maybe I'll go to a place where I need to wait for another event, and those places are signaled by that await instruction. And a coroutine is identified by that async instruction. While when the loop finishes checking one instruction, while it moves on to the next one. The benefit is you can handle much more concurrent things that you do than with threads. With threads, you're sort of limited to how many you can spawn. On a loop, you can attach a lot of tasks. This makes it ideal for network-limited things. So if you're calling APIs, probably you want to be using async. If you're developing a web server, you definitely need to be using async. So most of the modern web servers are actually using a version of async, maybe not in Python, but a similar programming construct. Limitations, well, you cannot use request. So if I'd have to implement that example I had at the beginning where I look up things on the Google Maps API, I couldn't use requests. I will need to use IAO HTTP. There's like actually an example if you guys are interested in. You need to explicitly handle exceptions. Otherwise, your task might just die and you don't get any input. And if you want to limit how many concurrent tasks can run at the same time, you need to use semaphores. So async, really useful for disk and network applications. Okay, what if I really need to, I'm really limited by CPU, running with all the processors in my machine doesn't work? Well, I could try PyPy. I can use it instead of calling Python, simply installed. And it's very attractive because I may not need to change my code at all. So I may not need to change any line in my code. How does it work? The interpreter itself is written in R Python, so restricted Python. This allows it to decide whether it needs to compile your instructions on the fly or not. This is called just-in-time compilation. So the interpreter can decide, okay, this instruction has been running several times, I'll just compile it. This instruction has been running just once, it just goes interpreter. The biggest benefits are for long-running processes, obviously, because then the interpreter has this time to actually gather the statistics and do it. limitations, just Python 2, the Python 3 is in beta. Not all libraries will work, and I'm sure you are aware that if you want to use NumPy with PyPy, you need to use a specific NumPy fork maintained by the PyPy community, at least for now. Sometimes you will need to tune the parameters, so you will need to tune the garbage collection in PyPy, and the RAM usage is very susceptible there. It's very sensible to this tuning. So you might end up using less RAM than not running in Python. You might end up using a lot more RAM than running in Python, depending on how you tune the PyPy interpreter. And this is why there are those two exclamative marks. It can go either way. You could get a bit of RAM back. You could end up using a lot more RAM. But it's definitely a win in terms of CPU. Well, what if I just want to win? Well, you could push your execution to C. There are C extensions. You just compile the slowest part of your program, but it means rewriting at least some parts of your program in C. What can you do? You can use Cython, which is a lighter weight solution. You pip install it, you call it with Cython. It has support for parallelizing operations. You define a function as a Cython function, as cdef, or as a Cython function with a Python wrapper with cpdef. You add some static types, and then you're ready to go. And you can get quite a huge speed up. So once again, the magic table of not so slow anymore. It's not going to solve all your problems all the time, but if you really don't know where to start, maybe this can help you. Thank you.
Thank you very much. Any questions? Anyone?
Hi, thanks very much for your talk. So on your magic table of not so slow anymore, RAM has lots of X's. So if I really care about optimizing RAM usage without trading off too much CPU or disk and network, what would be the best solution?
Running on, if your bottleneck is RAM, probably you are in a good place. So you probably don't, if you are running out of RAM, then you're probably in a bad place because your code is crashing. But if your problem is you cannot read and write fast enough from RAM, then you're probably in as good a place as you can be. Unless you're reading and writing a lot of stuff that you don't need to do, then you can maybe think about okay, am I doing the right operations? Am I using the right algorithm?
Thanks.
Hi, thanks for your talk. On the asynchronous front, do you have a preferred third-party library? Because all the async IO stuff in the standard library is pretty low level. It's not really meant to be used kind of as such, but it's more as a building block for people. Do you have a preference?
I tend to use it. So this is the full example. This is how I would use it. So if you have any good suggestion for libraries I could use to make this code fit in a slide, I will be so grateful.
I've seen people suggest Curio. Someone yesterday also said Trio. I was wondering if you've tried those and if there are any improvement. So my main pain point is taking this from here. Suppose you're gradually migrating to an asynchronous project. So I'm working on something that's quite big. It's making a lot of HTTP requests through requests. So that's all blocking and synchronous. And now we're gradually starting to migrate, and you find yourself having to go up the call stack and make everything async. Because the moment you replace one call, everything that calls that function all the way up to the main method needs to become asynchronous, and that breaks your program because there's a ton of scripts that call things. I guess that's partly because of bad design and using something as a library and as a standalone thing. But you eventually find out that the moment you make one thing asynchronous, it has to go all the way, and then everything just breaks.
So this is a very common problem with asynchronous. So you can probably find it in other languages as well. But once you decide that you want an event loop, well, that's your main thread of execution.
So do you know of any? Sorry.
Can you pick and choose, like, well, I want an event loop here, and then I want a normal control flow in another place? And
okay. Thank you.
We as Python developers just said it's a RAM problem, and also this yield instead of return saves a lot of memory and also a lot of your async returning issues. Use generators, and Curio is actually also using generators as coroutines, so that you can step by step go to a parallel world without the event loop. But RAM, if you run out of RAM, replace your returns by yields. It saves a lot.
Yes.
Do you have any experience extending Python with Rust?
No.
Okay.
No. Do you have that experience?
No, not really, but I was wondering if that works well or not.
Well, definitely threads don't have the same meaning that they have in other languages. I think, yeah, I'm not sure. Every language is sort of unique. It has like its own unique history of how it came to be.
Anything else? All right, thank you very much.
Thank you.